Hello class, welcome to Chapter 5, Integration. We look at sigma notation and limits of finite sums. In the previous lecture we saw finite sums and we did that using upper, lower or midpoint rule. And we're going to look at the extension of that, and in order to understand that we will use sigma notation. And so a quick look at what this means and how we use it to write terms, many terms in a compact manner. So just to begin off, I'll say sigma notation means we try to write the sum of terms in a compact manner. So it looks like this. Okay, sigma is like an exaggerated E. It's basically a Greek letter. It's similar to our S. And you have the AK, K1 to N. This is how we represent it. As you can see, it's compact for the fact that everything is self-explanatory here once we understand what this means. So this notation here, this is called sigma in Greek, or we simply call it the summation. In English, we like to use the word summation sometimes, especially in stats where we like to understand it as a sum, and so here in math too we use the summation symbol to indicate sigma. Then we have the index. Index is where the k values keep changing. It runs from 1 to n. So this will be the index. So and the index starts at k equals 1 because that's the lowest value it takes, and then the index ends, the index for k of course. It ends when k is n, it doesn't go past that. Okay. And this information in between, ak, that is the formula for the nth term. Therefore, summation ak, k equals 1 to n means it's a sum of all these ak terms. So k is 1, that's the beginning one, and it's always integers. So the next number after k equals 1 is k equals 2. You don't have any other real numbers in between that can be used. So it's only integers. So a2 plus a3 plus etc. plus an. So to add n terms, we have a1, a2, a3 and so on all the way to n, because that's your index. Your k ranges from 1 to n, and it takes all these whole numbers in between. Let's say we had to find summation k. Summation k. K is 1 to 5. How would you expand this? So k takes a value of 1 to begin with, and you have to do a plus because that's what the symbol means, summation. So you have to sum them. The next number will be 2 plus 3 plus 4 plus 5. You have to stop at 5 because that's where the index ends. Then sit and add them. Use a calculator. That gives us 15. And that will be the answer. So you don't have to write 1 plus 2 plus 3 plus 4 plus 5. You just say summation k 1 to 5. The answer is 15, and we would understand that. How about this? So this is the formula, right? So I could put in anything there and use that to expand for each term. Okay, so negative 1 power k times k. To expand this, I do negative 1 power 1 times 1 plus negative 1 power 2 times 2, and k is 3, that's where it ends, times 3. So it will be negative 1 plus 2 minus 3. The answer is negative 2. How about the next one here? K 1 to 2, K over K plus 1. And it doesn't have to be K, you know? I could use I and then use my index as I equals 1 to 2. You can use any letter. K, I are the more common ones that we use. So K is 1, so 1 over 1 plus 1, plus when K is 2, 2 over 2 plus 1. 1 over 2 plus 2 over 3. That gives us 7 over 6. Notice how here we start from 4 to 5, so it doesn't always have to start at 1. So this starts at 4, so it's going to be 4 squared over 4 minus 1 plus 5 squared over 5 minus 1. Take the LCD. Most often you'll be asked to give the answer as a fraction. So you kind of get the idea of how we use them. Now I'm going to put up some rules, and we'll remember to use those rules when we want to simplify expressions that are given in the sigma notation. Here are the algebra rules for finite sums. So you can separate them if they came out as a sum or as a difference. And if you had a multiple, you can pull the multiple out of the summation and only work on the ones that involve the k. And likewise, if you had to sum a constant over and over again, then it's the n times the constant. Okay, let's say you had to express the sum 1 plus 3 plus 5 plus 7 in sigma notation. How would you write this? Again, there are multiple answers that can be true for this. So you can think of summation k. I apologize, it was a plus 9 as well. Just put that in there. Plus 9. Okay, so we can go from. So you want to skip by 1, right? You want to add, but you have to skip 1. So if I just put a k, k will be 1, 2, 3, 4, etc. So I need to skip 1, which means if I can't do a minus 1, that will bring it down by 1, and still it will be continuous, right? It will be 1 below, but it will be continuous. So this doesn't work. So what happens if I did 2 times, because you're trying to skip 1 in between, right? So 2 times k will be, and k is 1, it will be 2. And what if I subtracted 1 from it? So 2 minus 1 will be 1. So that will give you the first term. When k is 2, 2 times 2 is 4. 4 minus 1 is 3. That gives you the next one. So you're going to tweak your answer based on, substituting different k values and trying different coefficients and so on. So this helps me out here. I can see that this is working. And it will work when k is 1. That's the first term. And I need to end at 9, right? So I need to make sure that I have the right number to end. So it's 9. So I'm thinking of k as 5. If k is 5, 2 times 5 is 10. 10 minus 1 will be 9. So I fix my my index to go from 1 to 5. Okay, this is one option. Okay. Can you think of another option? This is the most basic way of getting this. Well, I'm thinking, what if I did 2k plus 1? Can I justify this with a different index? So if we are going plus 1, then I have to start my index at 0, right? Meaning when k is 0, 2 times 0 is 0, 0 plus 1 is 1. That will give me the first term. When k is 1, 2 times 1 is 2, 2 plus 1, 3. So you're able to generate the same steps, but if you started at k equals 0. Because you're adding 1, I think we should stop at k equals 4. So that 4 times 2 is 8, 8 plus 1 is 9. So that also works. And then after this point, it's just, stretching it here and there. So we always put a parenthesis around it so that we know it's all being summed. Okay, what if I did 2k minus 3? So it is 2k minus 1 that I'm tweaking to write it as 2k minus 3. This variation offsets by 2, right? Yeah. So then my k has to start at 2. 2 times 2 is 4, 4 minus 3 is 1, right? So test it with the first value. And then because I've kind of increased my index by 1, what was 5 here, I increase it by 6 to test it. 2 times 6, 12, 12 minus 3, 9. Okay, that works. Yeah. Because your index is an integer, okay, you can do some extreme things like, I mean, we don't generally think like this, but I'm just trying to show you that there are multiple possible answers for this one. If I did a plus 7, so it is similar to this 2k plus 1, right? It's plus 7, I'm going a lot of numbers ahead. I don't need that many numbers ahead. So the only way I will adjust it is in my index. So my starting point, if k was, let's say, in this one k was 0, right? The starting point was 0 when it was plus 1. So I'm going to try negative 1. When k is negative, I need to go lower, right? To offset this plus 7. So negative 1 will be 2 times negative 1 will be negative 2 plus 7 will be a 5. And I don't want that 5 because we need to start at 1. So then I go for negative 2. 2 times negative 2 is negative 4. Negative 4 plus 7 will be a negative 3. So notice I got a 5, then I'm getting a 3. I need to start at 1. So I go 1 below. So what if I started at negative 3? Negative 3 times 2, negative 6 plus 7 is positive 1. Okay, I got my first term. In fact, when I was tweaking this or testing the starting point, I got the 3 and the 5 as well. So then I have to go, we saw 0 didn't work. I mean, 0 worked. In that it gave 7. Right? When k is 0, it will give us 7. So I need to go 1 above because I need to stop at 9, not at 7. So to go up to 9. When k is 1, 2 times 1 is 2, 2 plus 7 is 9. So you have these 4 answers. Now, if our question wanted us to find, say, summation k 1 to 3 k plus 4. Now we can use sum rule here, and sum rule says if you had a sum like this in your under your summation, then you can split them up as individual summations, individual sigmas. So that would be summation k 1 to 3 4. Summation k 1 to 3 is 1 plus 2 plus 3 plus summation 4 k 1 to 3. If you go back to the rules, it said if you are summing a constant, then all you have to do is simply do n times the c. So n here would be this end index, which is 3, and the constant is 4. Okay, so that will give us 18. Now what if we had to do summation k 1 to 3 k plus k squared? Same thing, 1 to 3 k plus summation k squared k 1 to 3. So for this you'll have to do 1 plus 2 plus 3, but here you'll have to do 1 squared plus 2 squared plus 3 squared. You need to compute all that to get the answer. Okay, and for that I'm going to give you a quick shortcut. If you had first n terms, summation k 1 to n, you could use this formula. If you had to sum squares, you could use this, and if you had to sum cubes, you could use this. So coming back to our problem, here it was pretty straightforward, so you could just go ahead and get the answer simply by adding them up. This would be a 6 plus 1 squared plus 4, 9, okay, 14, and that will give you 20. So you got that here. However, I can kind of illustrate that. Yeah, summation k 1 to 3, right? That's what we had. So if I were to use this formula, it would be n times n plus 1 over 2. N is 3, so 3 times 3 plus 1 over 2, which is 3 times 4 over 2, 6. And that's what we did. Because there were just 3 terms, we were able to add it. That seemed quicker than the formula, but you'll find this, or you'll appreciate this, you know, when you have to do even say up from 1 through 5, right? So that will be 5 times 5 plus 1, 6 over 2, and the answer is 15. And you see that that's a lot quicker because you don't have to take too long to substitute them, right? And for squared and the cube, the formula does look a little complicated. Actually, cubed is easier because it's just the same as summation k, and you just have to square that answer. But k squared is a little extra work. But again, you will find it helpful in examples that contain a large index. Okay, let's check out some examples on this. Sorry about that. K is 1 to n, so we're not giving you the end point, we just give you up to n. No problem, we use the difference formula. So k 1 to n, 3k minus summation k 1 to n k squared. And the 3 can be brought out because it's a constant. K squared. And you can actually stop here, or you could use the formula n times n plus 1 over 2, because you don't know what n is, so we just only can, you know, show the expansion for it, and when you have the n, then you can plug that in over 6. This is what you can do as a way to go further than the summation. Now if we were given summation, let's say k 1 to n negative ak, what we can do now is separate the negative as negative 1 times ak and treat that as a constant, and that can be brought out. Negative 1 summation k 1 to n ak, because remember, constant multiple rule says if you have a term that does not contain k in it, then that is a constant and can be pulled out outside the summation, so we can focus only on adding the ones that involve k. So summation k 1 to n 1 over n. Look at this expression. The formula here, 1 over n, does not contain k in it, so it's as if it's a constant. So the constant rule says you multiply this index n times the formula, or the constant in this case, n times 1 over n, and the answer is 1. The next concept is to find the limits of finite sums, and we found that finite sums are nothing but approximation of the area by constructing rectangles. And we also saw the sigma notation just now, where you could write these finite sums using the summation notation. And now we want to develop to the idea of limits of these finite sums, and so we begin with the approach of approximating area. So what we did was we took the interval and we divided it into so many partitions, right? Because we just decided how many rectangles we wanted, and we divided it that way. So that's what I'm going to explain here. So say if we divide an interval usually we denote it by AB, into n partitions. Right? If we wanted 2 rectangles, it will be 2 partitions. If we wanted 4 rectangles, 4 partitions, and so on. So n. We will choose n minus 1 points. Okay, now think about this. Where did this n minus 1 come from? Now you want to, you have a stick, okay? you have a stick and you want to break it into 2 equal parts. How many places will you break the stick? You'll only break the stick in one place, right? So that if you had one stick like this, you break it in the middle so that you get 2 pieces. So you only have to look at one point. Even though you want 2 partitions, you're looking at only one point. How will you break a stick into 3 parts? So you break it in 2 places so that you get 3 parts, 3 pieces of that stick. So although you want 3, 1, 2, 3, you're only looking at 2 places, 1 and 2. That is how we get the n minus 1. So if I want n partitions, I need n minus 1 points to break it into n parts. And that is true, right? We did this example where we divided this region into 4 parts. Okay, I want to break this into 4 parts. Okay, we did 1 minus 0 over 4 and we got 1/4. Right? So 0 plus 1/4 is 1/4. 1/4 plus 1/4, 1/2. 1/2 plus 1/4 is 3/4. 3/4 plus 1/4 will be 1. So technically speaking, we got 3 points to get 1, 2, 3, 4 subintervals. And that is what we mean by we choose n minus 1 points. Okay. All right, now we have partitions, and we can call P x0, x1, x2, etc. xn minus 1 and xn is called a partition of AB. Let me illustrate this on a number line now, because you now have the endpoints as well. So your number line goes on, but then you do have your A, and this is your B, right? All this is happening in the interval A to B. But we know that A is now given x0 as the starting point, so that this will be x1, x2, x3. This is some kth interval xk. This will be xn minus 1, 1 before the end point, and the endpoint B will be your xn. Okay, that way it's all in x's, so we don't have the A and the B. We do know that x0 is A and xn is B. These are all the points. Okay, these are all the points, the x values, I would say, x values there. But if you wanted if you wanted n partitions, you need n minus 1 points, because these are the end points, right? So you need n minus 1 points in between them. Okay. So now our focus would be to look at one particular interval. Okay. And if we can focus on one particular interval, which would represent one particular rectangle, right? Remember, these are the intervals over which you're going to construct rectangles. So you're going to do this depending on the graph above it. So that is the underlying, the background information that we have. So I want to focus on the kth interval. A kth interval would be some arbitrary interval, right? So we're not looking at the first, we're not looking at the third, we can look at any kth interval. And so for that, we see that this would be that specific kth interval. Okay, so I'm going to call it, this whole thing is A to B is called the interval, so let me just call it the kth subinterval. Okay. Now, what do you think could be the width of these? So if you consider the width of these between x0 and x1, okay, this will be the width, and let me call it, and we indicate the width, you remember, the change or the difference in the axis as delta. So I'm going to call this delta x1, okay, meaning that is the width of the first interval. This will be the first interval, isn't it? First, I could say subinterval. And for this one it will be delta x2 to indicate the width of the second interval. So I'll just say delta x1 is the width of first subinterval. This is the width of second subinterval, and so on, xk minus 1 to xk. That will be delta xk, making it the width of the kth subinterval. This is important because remember there'll be a rectangle above this. So if there's a rectangle above this, we need to find the length times the width in order to get the area, and so the width is first determined. This is going to be delta xk, the kth interval's width. And if need be, you can also consider this. The last one will be delta xn, isn't it? Because that is the nth interval, the last one. Okay? Now our question is, well, there is going to be a graph because this is just the x-axis, but if you were to stretch it out, you'll actually see the graph running through all these, right? So when I have a graph through these points, up and down the x-axis, but I will now have to construct the rectangle or touching these, the rectangles must touch the graph. So the question is, should I do the upper or should I do the lower or the midpoint, isn't it? But one thing is clear, doesn't matter whatever technique we use, we just have to get a lot of rectangles. You can't just have a few rectangles because that will compromise the estimate value. Assume that this was the graph, okay, and you were asked to find the area under the curve up to the x-axis. So if we kind of mimic what we had up there, right, this will be x0, and then this will be x1, x2, x3, and so on. Let's say this was xk, this will be xn, and that one before that will be xn minus 1, one before this will be xk minus 1, and so on. If I were to construct rectangles for the lower sum, then remember lower sum is left end, and so my rectangles would be coming from the left end point like this. Yeah, and I go on constructing them like that. If I was estimating it using the upper sum, then we would be going on by the right end point. Oops, I went too far off. And so on. By the right end point, that's how you build your, so that's overestimating, it goes outside the curve. And if we use the midpoint rule, it's a little tricky, but something like this. Midpoint of the rectangle point passes through the, touches the blue curve. So we see it doesn't matter how we divide this, but we want to make sure that they are really thin rectangles. So let me just reiterate that point. I'll say finer partitions implies you get thin rectangles with thin bases, right? The base is thin. And if the base is thin, then it assures you that your rectangle is skinny. And this implies the region is approximation is closer to the true value. In this case, the true area. Alright, so for the sake of this example, I have it as these rectangles constructed through the midpoints, but it doesn't look exactly as midpoints in some of these rectangles, and that is there for a reason. Okay, so what happens is, if I were to, so I know this is looking more like the midpoint, but let's say if you had to do the left end point approximation. So this is for the lower sum. So if that was the case, then our rectangle would be, this is lower, right? So it must be below the curve. So it can't go above the curve, it has to stay below the curve. So you can think of this as a rectangle. Okay, I'm using blue, so I'm going to use a different color. This would be a rectangle, right? And then the next one would be this. I hope you're able to see or track along with me. So that is how we would be constructing them, so which means the left endpoints are considered. So let me not clutter that. If the left endpoints are considered, then we would be looking at the rectangle with x0 as the left hand point, right? x1 as the left hand point, assuming that you shifted your rectangles to stay under the curve. So our intervals would be x0 to x1, x1 to x2, etc., xn minus 1 to xn, right? And the width here would be delta x1, this will be delta x2, this will be delta xn. Okay. Now again, we are looking at any width, okay, because we just are trying to build up to the equal width. So this could be any width to reiterate our point. So the area, so let's just focus on the kth interval, kth subinterval. So for that kth subinterval, okay, that's going to happen here, right? So xk minus 1 to xk, that will be the kth subinterval with delta xk. So the area for that kth interval, okay, so this is like the kth box. So let's say you were focusing on this kth interval. Okay. And let me highlight that for you. Assume the rectangle looked like this, not the pink one. Then what happens is we have the left end point, okay, left end point, this would have been xk minus 1, not there, but it would have been here, right? So xk minus 1, its corresponding a point would be f of xk minus 1. This would be the height, and delta xk would be the width of the rectangle. That means area of kth rectangle will be f of xk minus 1 times delta xk. Does that make sense? Okay, so we have these two, and this is just any kth interval, right? So if this was the case, then you'll take the sum of all these rectangles using the left hand point, and if you added all those areas, you will get, so the sum of the partitions, we call it SP. Okay, so that will be sum of all k from 1 to n, f of xk minus 1 delta xk, isn't it? And what we're saying is, let's say for convenience and uniformity, let the width be equal for every subinterval. If that's the case, then it's not going to vary by delta x1, delta x2. They'll all be the same delta x, right? They will all be the same width. So delta xk would simply be b minus a over n, because that's how we found the equal width, and that's how your delta xk will be defined. Now if I want to get to xk minus 1, okay, this position, if I want to get to xk minus 1, I should have a formula that does not involve intermediate points, but it involves the endpoints and the n, because you know you want to use what you have, not go in and look at the k minus 1, because nobody knows what that value is. It's an arbitrary point. So I'm going to take you back to the to this graph here. So if I need to get xk minus 1, what I know is that I have to start here at a and then add this distance, right, to get to this xk minus 1, which is the left end of my of the interval. So how do I get there? So if I looked at so that's basically x naught plus this distance, right, this width plus this width plus this width. And because we know that all these widths are the same, we now can see that the width will be in each case b minus a over n. Now quickly count how many boxes or how many rectangles will be crossed to get the width. So we will have, this is the first rectangle, second, third, fourth, fifth, and so on up to the kth rectangle, right? We'll get to the kth rectangle, but remember k minus 1 to xk is the kth width. But we will stop one before that because we're only going up to the k minus 1 end, right? Up to this end. So we'll go a plus b minus a over n, b minus a over n, b minus a, adding all of those, but you'll stop one before the kth interval. So xk minus 1 will be a plus k minus 1 times b minus a over n. Okay, why? Because I'll just explain that here, which is the same as, or maybe I should explain it right here and then simplify it. B minus a over n plus b minus a over n plus b minus a over n. This is what's happening. Okay, so then this will be the width delta x1, this is delta x2, this is delta x3, and so on, and we stop not at delta xk but xk minus 1, the previous one. Okay, that means you have each of them are equal width, so you're adding b minus a over n k minus 1 times, and that's what I meant in the previous step when I did k minus 1 times b minus a over n. This is k minus 1. So if I wrote SP, then if you go back here, SP is summation of all these areas 1 to n, f of xk minus 1. Now in the place of k minus 1 I have a plus k minus 1 times b minus a over n times the delta xk is b minus a over n, b minus a over n. Okay, this is for lower sum left endpoint approximation. Do we agree with that? The reason I rewrote the xk minus 1 and the xk was to eliminate any particular x value and to use only the b and the a, the endpoints of your interval, and how many subdivisions you are creating, like in this case it is n. So that is all we used to develop this, and because it was ranging from 1 to n, we used the letter k in the formula. So this is really neat. The formula looks a little more expanded as opposed to xk minus 1 and xk, but actually speaking, when you are presented with a problem, you can kind of complete this by just using the endpoints and the n. And that is really important. Now what about finding for the upper sum? Okay. So I'm going to go up to our diagram here, clear all this, and then see what happens if it was an upper sum. Okay. If it was an upper sum, we will be looking at the right endpoint. Okay. So this would have been my case. So the right endpoint. The next rectangle would have been here, right, like this, and so on. So anyway, I'll just keep the first one, and then I'll go to the kth one. Okay. So the right endpoint would have looked like this for the kth interval. Again, I would like you to assume that this is xk minus 1, but this end here is xk. I'd like you to assume that, so that this is like our rectangle of interest, where the left end of this rectangle is xk minus 1 and the right end is xk, and of course our right or the upper sum would be the right end approximation, right endpoint approximation. Okay, so the kth interval. So you can argue the same way, right? The kth subinterval. The kth subinterval will have the height that corresponds to xk, isn't it? Because it's the right endpoint. Previously it was the xk minus 1, so here it's xk. So I'll come back here and I'll say upper sum right endpoint approximation. So for the kth subinterval, the height is f of xk. Okay, notice it's xk. It is not any. It's the. So in your kth interval, this is xk minus 1. This is xk, and it is this place where when the graph goes, that's the rectangle that you're forming. And the width is delta xk, because we're still in the kth subinterval, so it's delta xk. And so if you did the SP, it was summation k 1 to n, sum of all the areas of the rectangle. So area of the kth rectangle is length or height times the width. So f of xk times delta xk. Now remember, we have to replace the xk with the endpoints. A way to rewrite it using the endpoints. So, with the equal width, once again delta xk will become b minus a over n. No problem there. It's this xk that I will have to represent now, so for which I go back to the diagram. Okay, so we start at a, okay, a, and I have to add this region. I need to go from A all the way up to this end point, okay, up to the right end point. Notice how the yellow shaded rectangle is included. Previously, we stopped just before the rectangle was considered, before the yellow shaded rectangle began. But here it is at the end of the rectangle. So we are ending at xk. So if you think of this, you start at A, so A plus, this is the starting point, A plus this width plus next width and etc., including the yellow rectangle which is of width delta k. Because it includes delta k, we will we'll have the widths or the base of k rectangles, not k minus 1 but k rectangles. So like before, I'm going to expand this for us. So it's going to be a plus b minus a over n plus b minus a over n plus b minus a over n, and so on. It looks very, very much, in fact it looks identical like the previous one, but the way we understand this is the width, equal width, right? So this is the width of the first interval, this is the width of the second interval, the third interval, and so on, and this will be the kth interval because the yellow shaded rectangle was also included. That's why we ended on the right end point, and therefore this can be collectively written as a plus k times b minus a over n. So once you have that, we rewrite the SP summation k 1 to n f of, in the place of xk, this is xk, right? Right, as a plus k times b minus a over n times b minus a over n for the delta x. Delta xk will be b minus a over n. And this is the formula we use for upper sum right end approximation. Notice that the only difference was for the left end you had k minus 1, here you have k. We can quickly check that out. Yes, we do have the k minus 1 coming in there. Here we have the k. Alright, so what happens if we were to use the midpoint? So I don't have to do all this because you've seen it twice now. We can actually do it more analytically without having to look at it each time. So for that, you can actually consider this very rectangle we have, right? So we can say this is the kth one, and xk minus 1, xk are in the right positions, and ck is the midpoint of that rectangle. So it's the midpoint of that interval. ck is the midpoint of the kth subinterval, right? Therefore, the height of the rectangle will be the f of ck. The corresponding y coordinate of ck will give us the height of this rectangle. Let me shade this. Okay. So then when I want to write this ck will go all the way from here to the middle of my rectangle, right, to the middle. So for the left hand point, it stopped at xk minus 1. For the right hand point, it went all the way to xk. And for the midpoint, it stops obviously at the midpoint. So I'll have delta x1, delta x2, delta x3, etc., delta xk, but only half of delta xk. I can't use all of the width, only half of that width. So that is the adjustment I'm going to bring in for midpoint. So let me write that down here. For midpoint rule, and within the kth subinterval, ck is the midpoint. Okay. So if everything else will be pretty much the same, right? Length times the width and all that. The only place where we will have everywhere we said xk, but here we're going to call it ck. That's another difference. So sp would be summation k 1 to n, f of ck because it's going to be the height, times delta xk because it's still the kth subinterval. And then for ck, we have a plus b minus a over n plus b minus a over n b minus a over n plus half of b minus a over n. So again, a quick explanation will tell us that this was the width of the first interval. This is the width of the second interval, third interval. This is half the width of the kth interval because you only go up to the midpoint. Therefore, collectively, this will be a plus. You have you can look at it in two ways. You can do k times b minus a minus a half, or just k minus half, right? So you have k. That was k minus 1, isn't it? This is k minus half. Just put my b minus a. So then this sp will be summation k. Sp is the sum of the partition, right? K 1 to n, f of ck, and in the place of ck I now have a plus k minus half, b minus a over n, b minus a over n. Okay, looks lengthy. Okay, this is for midpoint rule. Let me also box this. You can later on, move the video ahead and back and forth to kind of see that the big difference was for left hand point it was k minus 1, right hand point it was k, and for midpoint it's k minus half. So everything else remains the same. It's just this k that keeps moving. So will this change if we were to use any particular method? Will this affect if we used any particular method over the other? This is where we have Riemann sum concept really helping us. So Riemann says, well, if you had a subinterval, the kth subinterval, right? We shouldn't be worried about choosing the left endpoint or the right endpoint or the midpoint. For that matter, it doesn't matter any point that you choose on the subinterval, because this would become insignificant. Doesn't matter which endpoint you're using, it becomes insignificant when we choose our rectangles to be really, really, really fine. If they are really so thin, it really doesn't matter which point we're using, because you are making it extraordinarily thin, and the width is almost negligent, where it doesn't matter where you choose your point. So what Riemann said was, for any point xi in the interval in fact, there's a little star that they use. So xi minus 1 to xi to xi. This is the notation that he used. For our sake, we could just say xk, right? So xk with a star, and then we could say that belongs, remember the symbol? That belongs to the interval xk minus 1 to xk. And so all he said was, well, all you have to do is understand that the area will be approximately equal to summation I 1 to n f of xi with that star, because xi is any value in the interval. So it could be the end point, could be the left end point, it could be the right end point, midpoint, or any other point, right? Delta x. No xk, because delta x kind of tells us that it's all uniform. So it doesn't matter if it's the kth interval or the first interval or the nth interval, they all have the same width. Okay. And so if we wanted to write it in terms of k, no problem. We have 1 to k f of x k with a star delta x. And this will hold true if we have very fine partitions where the rectangles are extremely thin with thin base. And this is true. In fact, Riemann actually compared, finding the area of the rectangle for different endpoints, and he kept increasing the number of partitions. Then he found that it didn't matter which technique we used, we always got the answers very close to each other. And it was based on his observation, his experimentation, his computation that he was able to present this idea, this concept. So there is actually a definition for this, and you will see that now. The definition says, let f of x be defined on a closed interval AB, and let P be a regular partition of AB. Let delta x be the width of each subinterval xi minus 1 to xi, and for each I, let xi star be any point in this interval xi minus 1 to xi. A Riemann sum is defined for f of x as summation I 1 to n f of xi star times delta x, the very thing we wrote above and which I explained. Okay, the key thing is he's saying this n, right, the number of partitions, must be really, really, really small. For n to be really, really, really small, you can't have a small number of n, you can only have large number of n, right? So if you want a thin rectangle, you can't divide the interval into 2, but if you divide it into 4, you get a thinner slice of a rectangle. If you divide it into 8, it's thinner, into 16, it's really thinner. So you can see that as n gets larger and larger, we are promised a series of thin rectangles of equal width. Okay, so as n gets larger and larger, the rectangles get thinner and thinner, and that is when the assurance of Raimann's sum holds true, where he says doesn't matter where you choose your x value, doesn't have to be left end, right end, doesn't matter. For that to be true, we want to get n to be really large. And remember, in calculus, we want n to be really large. We allow n to approach infinity, and that means we are talking about limits. Okay, limit as n approaches infinity. And so we have this formula that's modified. Okay, now this is for one rectangle, right? This is the area of the ith rectangle. We say k, but here they used I, so I'll say ith rectangle. And if we added all the areas of the rectangle, so I mean this part alone is the ith rectangle, and when I ranges from 1 to n, the whole thing gives you the, let me write that also, this whole thing gives you the area of all the rectangles. Yeah, so the formula inside, that is the area of the ith rectangle, but when you sum it, you get all the rectangles. So then this leads us to the definition here, where we it says, let f of x be a continuous non-negative function on an interval ab, and let summation I 1 to n f of xi star delta x be a Riemann sum for f of x. We just saw that. Then the area under the curve y equals f of x is given by a equals limit summation f of xi star times delta x. Okay, this is really in a nutshell, so I just feel like I should explain this a little bit more. Riemann sum is this. The sum is I 1 to n f of xi star delta x. Okay, so Riemann sum is the sum of all rectangles. So it's an approximation. Now we're saying as n approaches infinity, Riemann sum becomes the actual, I shouldn't say actual, I should say exact. Becomes the exact area under the curve. Remember, we've been doing approximation all along, but we're saying if you allow n to go to infinity, so you have infinitely thin, extremely thin rectangles, then you're basically looking at the area under the curve. Does that make sense? And so that is what we mean by A equals, this is Riemann sum, and in front of Riemann sum we take the limit as n approaches infinity. So limit of Riemann sum gives us the exact area. So limit as n approaches infinity of Riemann sum is the area under the curve. And this is amazing because it gives you the exact area because of the fact that you are able to use limits to allow n to go to infinity. And this, my friends, is the birth of integration. Just like how we saw in derivatives, where we took the limit of dq, limit of the difference quotient, and found that to be a derivative. Here, the limit of Riemann sum becomes our integration. We'll be looking at this in the next lecture, of course, where we'll be using special symbols to do this. But I hope you were able to understand the background of how we find the area under the curve from an approximation, we've reached to a point where we can get the exact area. See you in the next video.